This is the fourth installment of our videos on graphing quadratic functions, and it's the last big thing that we need to cover. Now, all the parts that we've done so far, y-intercept, finding a vertex, finding these values using our calculator, it's something that we're going to have to do with all kinds of functions. This is just where we start in this course with quadratic functions. Recall that quadratic functions are functions that have one variable of x. It could be some other variable, but just one variable, and the highest exponential value it has is 2, and it has to have the 2. Now, this particular installment talks about domain and range. Every function has a domain and it has a range. In its most simplest definition, domain is x values of a function, and the range are y values. And you've probably heard that before and know that, but what does that look like on the graph? That's what you need to see. Now, pause the video, graph this function, and let's talk about the domain and the range and how we would find that by looking at the graph, and how we would show that using algebraic notation. Alright, so we've got the function in the calculator, negative x squared plus 2x plus 3. Always double check it just to make sure it's right. If we look at the graph, we're looking for the domain and the range. Now, I don't need to go into the table. I don't need to worry about the vertex. Well, I do. The vertex is going to help me find my range. Now, the domain we've said are x values. Now, when I look at this screen, it looks like the x values are like between negative 3 and 1, 2, 3, 4, 5. But that's only because that's all I can see here. If I go into the table, I can see that the x values, as long as I hold this down, it's going to keep on going. If I want to change that x value to 570, it's going to have some value for y. So the only thing I really need to look for the domain is, are there any values of x that I can't use? I don't see any errors here. I don't have any dividing or anything going on over here. My goodness, it wouldn't even be a quadratic function. So I'm just looking to see if there are any breaks. I can see that in the table, and I'd be able to see that on the graph too if there were some kind of break where it just kind of stopped and then picked up again somewhere else. But that comes with other kinds of functions. Now, the range of the function is, what are the y values? Now, when I look at this, I know that this is going to go on and on and on, as negative as it can get, and I'm not going to see how low it can go, but I can see how high it can go. And I know that the y value is never going to go above this. I suspect by looking, just by eyeballing it, that 1, 2, 3, 4 looks like it might be the highest it goes, but I need to verify that it's not 4.2 or 4.5, but that it's actually 4. And I can do that by looking at the table, look for the 4 that I think it is, and see I have symmetry on both sides of that 4, so that is the highest value because it is the vertex, and that contains the maximum value. So, all quadratic functions are going to have a domain of all real numbers, and you can write it like that. But all quadratic functions will not have a range of all real numbers, because our range, we're going to have a maximum or a minimum value. It's not going to just go on and on and on. But on this one, I know that the maximum value that this function is going to have is this 4. I can only see that in the table if I see the symmetry on both sides. Because I see that symmetry, I can say that the range is all real numbers less than or equal to 4. In this case, it's 4, but to the maximum value. This is what that looks like in algebraic notation, and you need to be able to do this. The set of all numbers, all values of the function, such that the values of the function are always going to be less than or equal to 4. Rewind that and hear that again if you need to hear that, but that's what that means. All real numbers less than or equal to 4, this is stated the set of all values of the function such that values of the function are less than or equal to 4. Therefore, the domain represented by capital D equals the set of all real numbers. The range equals the set of all values of the function such that the values of the function are less than or equal to 4. This is just one example of what you look for when you're finding the domain and range, but that's what you look for. If that function were, for example, instead of a parabola that points down, perhaps it would just be a parabola that did not have that opened up. And if the parabola opened up, I would not have a function, the range where the values of the function have to be less than or equal to 4. It's never going to be less than, looks like about 2 here. So this particular function would be, the domain would still be all real numbers because it's quadratic, and the domain of all quadratic functions are all real numbers. But the range would be the values of the function f of x such that f of x, look for some symmetry here, get a real good look at it, looks like 2, just like I thought it looked like, 3, 3, 6, 11, 18, 6, 11, 18. The lowest it's going to go is 2. So what that would look like is f of x such that f of x is greater than or equal to 2. And you can see that all the values of the function, everything in here is going to be on that function is greater than or equal to 2, or everything in this table is greater than or equal to 2. And that's domain or range.